Good morning, dear students. Welcome to another session of microwave and antenna. So, in the previous session, we started off our discussion pertaining to point sources. So, in this case, we discussed regarding what is a point source and how we can make the observations with respect to the radiation which is being emitted. There are two methods, that is what we discussed in this case. Then after that, we went ahead with discussion pertaining to radiation pattern. That is, in that we discussed regarding what is meant by power pattern, in that what is absolute power pattern, what is relative power pattern, and what is normalized power pattern. Then apart from that, we also discussed regarding the radiation intensity and pattern associated with radiation intensity. So these were the discussions what we had done in the previous session. Along with that, we discussed power theorem in terms of the power density and the radiation intensity. So these were the two discussions which we had done in the previous session. So that is the point sources. So with respect to this, we had the discussion antenna and the observation circle. Then what is power pattern? Why r theta phi is referred over here? That is, we are considering an antenna at the center, and we are trying to identify at a particular distance what is the radiation which is available, or what is the field or intensity which is available. So which will be your spherical coordinate system. So, and we had discussion pertaining to this, that is what is the absolute power pattern, what is the relative power pattern, what is a normalized power pattern. So these aspects we have discussed, and we had discussed power theorem and its application to isotropic antenna, in which we saw that when power density is given, how I can move ahead, and when radiation intensity is specified, how I can move ahead. So these are the two aspects what we have discussed. So now, moving ahead, let us see whether we can apply power theorem concept to identify the directivity of a given antenna. So the first problem which we have is a source with unidirectional cosine pattern. There is a source with unidirectional cosine pattern. We need to identify what is the directivity of this antenna, which is having unidirectional cosine power pattern. So what we will be considering is, we'll be considering this pattern, what is given over here as the intensity pattern, that is radiation intensity pattern. So we need to apply that concept, and then we need to identify what is the directivity. Now, in previous discussions, we had seen, by definition of directivity in terms of radiation intensity, it is given as the ratio of maximum radiation intensity to average radiation intensity. So this is by definition what is directivity. Now I make use of this definition itself in order to identify what is the directivity for the given power pattern. So how do I obtain um, and how do I obtain u naught, or indirectly how do I obtain this ratio? So that is what we have to look out for. Now, as I had discussed in previous session, right? If you remember, if I'm considering the elevation angle or the theta angle, so if it is in the range of 0 to pi, that is complete 180 degrees elevation angle. If the entire angle is considered, that is from 0 to pi, then we specify it as full sphere. We specify it as full sphere. And if we consider the hemisphere, in which the variation of theta will be in the range of 0 to pi by 2. This is 0 to 180 degrees. This will be 0 to 90 degrees. So this will give you half sphere or semisphere. So it will be half sphere or the hemisphere. So now when do I consider this condition and when do I consider this condition? Now what happens is you get you come across this term which is termed as unidirectional antenna. So you can have unidirectional or bidirectional antennas. So in these cases, what is the angle I need to consider? Now remember, if it is a unidirectional antenna, so it is assumed that the antenna is radiating from say 0 degrees to 90 degrees. So if this is the theta, if I'm considering, say if theta is equal to 0 to 90 degrees. So if an antenna is placed over here, and if I measure the radiation intensity, I'll be having values over here. And apart from that, if you move in the other directions, that is, say if I extend it, if you draw the coordinate system, right? If you draw the coordinate system, so that is here we have it. So this case, in this case, you can see that we have phi and we have theta. That is, in this case, theta is in the range of what? It is 0 here, it is 90 degrees here, and it is 180 degrees. Now, as per the specification in unidirectional antenna, what happens? Theta variation, that is the angle, is with respect to 0 to 90 degrees. So, what is that implying? In unidirectional antenna, the variation is present or the field is present only in the half hemisphere. So, for that purpose, what happens is you have to consider theta from 0 to 90 degrees. And when I move further, right, when I move further, that is from 90 to 180, I'll be not having any radiation which is available. So it is implied that it is 0 in that direction. Now even in the other direction, when I measure, it will be from 0 to 90 degrees. Here I'll be having the values, but if I continue from 90 to 180 degrees, I'll be having radiation which is 0. So this is what is happening is radiation is present only in the half hemisphere. So for that purpose, if I just happen to show, so if I happen to show with respect to this, so here I can see what is happening is, so if an antenna is placed over here, just as an example, and if I measure the values of this intensity, say in this case, what is done is this is 0 and this is say from this side, this is sorry, theta is equal to 0 degrees, theta is equal to 90 degrees. When I make the measurement, I'll be having only values around this angle. If I try to measure below, right, I'll not be having any values over here. So this is what the half sphere implies. Okay, that is radiation will be present only in the half sphere. So if I consider the entire sphere, right, that is the antenna which is under consideration is bidirectional. It is not unidirectional. In that, what happens is, in that we'll be having variation for theta is equal to 0 degrees to theta equal to 180 degrees. So in this case, if I measure the values around the theta from 0 to 180 degrees, I'll be having some values of that radiation intensity. Similarly, if I move in the other anticlockwise direction from 0 to 180 degrees, I'll be having values over here. So in unidirectional antenna, so the major concept is, if I consider unidirectional antenna, If I consider unidirectional antenna, theta will be in the range of 0 to 90 degrees. But if it is bidirectional, it will be 0 to 180 degrees. So now let us move ahead with the problem. Source is having unidirectional cosine pattern. So he is specifying that the pattern is unidirectional and the pattern is in the form of sine. So for such cases, what we do is we can represent the radiation intensity, which gives you the pattern information as cos theta, as cos theta. So this gives me what? This tells me that the intensity pattern is cosine in nature. Now, what is the maximum value of this? This generally what I do is we assume one particular value, say maximum value is um. Maximum value is um. So this is indicating that this is having the cosine pattern and it is having a maximum value of um. And how do I identify that it is unidirectional? I specify the value of theta. Theta is in the range of 0 to 90 degrees, which gives us an indication that this is a unidirectional antenna, and phi will be in the range of 0 to 2 pi. So this is the radiation pattern for the given antenna. For this antenna, I need to identify what is the directivity. So for this case, if I try to just plot it, if I try to plot this, so if I consider say theta is equal to 0 degrees and theta is equal to 90 degrees over here. So if I consider this, what I'll be having is if I just substitute the theta values at all possible values from 0 to 90 degrees, I'll be having the value which is represented over by this equation. So what is cos 0? Cos 0 is 1. So therefore what happens is 1 into um. So this value will be maximum. And if I substitute theta equal to 90 degrees, it will be 0. So I'll be having a value of 0 over here. So it will be actually a plot will be there, which we call as polar plot. And when we plot it, we'll be getting this kind of pattern. So, and at 45 degrees. So with respect to angle itself, we try to identify what is the radiation pattern. So if the antenna is here, so along 0 degrees, I am having maximum. And at 90 degrees, I am having 0. Then if I say measure with respect to 45 degrees, it is around 1 by square root of 2, which will be somewhere here. So if this is the 45 degrees angle, it will be somewhere here. And when I plot this, so similarly, I have to identify at the other end also from 0 to 90 degrees. So it will be maximum over here. At 45, it will be 1 by square root of 2. And at 90 degrees, it will be 0. So when I plot this, I just combine these lines. So I'll be having a pattern which will be appearing in this form. That is, this is how it will be appearing. So this is just a plot. So, and for other angles, right, the value will be 0. For the angles, it will be 0. So now once I have written the equation for the pattern which we have specified, that is unidirectional cosine power pattern, I have to identify the directivity. So in order to identify the directivity, I have to obtain the ratio maximum radiation intensity to average radiation intensity. Next assumption what we look out is we assume that U naught is the average radiation intensity which is emitted by the antenna which is under consideration. U naught will be the average radiation intensity which is emitted by the antenna under consideration. When we consider this case, right, we are assuming that this is the radiation intensity which will generally be emitted by the isotropic antenna. So the average value of radiation intensity will be equal to the average value of radiation intensity which is being emitted by the isotropic antenna. So based on that, yesterday we had applied power theorem. So in which based on radiation intensity, what we had radiation intensity is the integral of the solid angle of radiation intensity with respect to the solid angle. It is integration of the radiation intensity with respect to solid angle. Now, if it is an isotropic antenna, what we had, if it is an isotropic antenna, what we have it as a double integration of, this will be a constant value, which is u naught, and d omega is what? It is sine theta d theta d phi, and theta is varying in the range of 0 to 2 pi, and phi is varying in the range of 0 to 2 pi. So this is for the isotropic antenna. So here when we simplify it, we get the solution of the integral as 4 pi. So which we had written it as what? We had written it as, so we had obtained the equation as 4 pi u naught. So this will be the power which will be radiated by the antenna, if I assume that it is an isotropic antenna. So this is with respect to the average radiation intensity which can be emitted by the antenna under consideration, which will be nearly equal to that of the isotropic antenna. So this is one assumption what we have to make when we are doing this calculation. So here radiation intensity U naught is the radiation intensity due to the isotropic antenna, and because of application of power theorem, we had obtained P is equal to 4 pi U naught. Now, what is the total power which has been radiated because of this pattern? That is what we have to estimate now. So first estimation, we got what is the total power radiated because of the isotropic antenna which is under consideration. So which is given by 4 pi U naught. So now because of this pattern, we need to identify what is the total power. Now again, we apply the power theorem. So here power theorem will give me the total power which is being radiated by the antenna under consideration. So in this case, what I'll be having the double integration of radiation intensity with respect to d omega, with respect to d omega. D omega is what? It is sine theta d theta d phi. Now u is given by this equation. U is given by this equation. So now you substitute for theta and phi values. So u is um cos theta. Theta varies from 0 to pi by 2 and phi varies from 0 to 2 pi. And the rest part is d omega, that is sine theta d phi. Now you can use any of the concepts, that is substitution method or simplification method, or use gamma and beta functions to obtain the integration result, so that you can do over here. So when you're performing this, when we simplify the integral, so in this case what we have done, we have taken 2 times sine theta cos theta is equal to sine 2 theta. So that is, we have replaced this cos theta into sine theta by sine 2 theta by 2. So what is integration of sine? It is minus cos, and since we have 2 theta again inside, it will be divided by 2. So the what we'll be having, we will have is a constant value, therefore we have taken it outside, and this 2 we have taken it outside, and what we have, integration of phi is equal to 0 to 2 pi with respect to d phi. Here I am not having any phi component, so integration of that will be nothing but phi, and the limits will be 2 pi to 0, and integration of sine 2, this 2 is already taken outside, it is outside. So it is integration of sine 2 theta is minus cos 2 theta, and since inside again we have 2 theta, it will be divided by 2. That is this value. It is divided by 2, and the limits are pi by 2 to 0. So when we solve this equation, what I'll be having is, I'll be having the total power radiated by the antenna which is under consideration, which is having the unidirectional cosine pattern, is given by pi into um. It is given by pi into um. So now what we have total 2 equations. One is the total power which is radiated by the antenna under consideration, and the total power which is radiated by considering a isotropic antenna, in which it is the assumption that U naught will be the value of the average radiation which will be emitted by this antenna. That is the consideration. So in short, we specify the this is the power which has been radiated by the isotropic antenna, and this is the power which has been radiated by the antenna under consideration. Now what we assume is, we assume that we equate this power equal to this power, and try to obtain what is the directivity. So when we equate both the equations, what we have, so this is due to the antenna under consideration, and this is due to the isotropic antenna. So if we equate these two equations, what we'll be having pi times um into 4 pi times u naught. Now I want a ratio of um by u naught. So um by u naught will be equal to 4. So this is nothing but the directivity of the antenna. This is nothing but the directivity of the antenna. So remember, here directivity is in the range of what? Directivity is greater than equal to 1. It cannot be less than 1. So if you're getting the value as less than 1, then somewhere calculation mistakes might be there. So you can rectify those things. So now let us estimate what is the directivity when the pattern is bidirectional and when we have the cosine pattern. So now in this case, again, how do I identify that it is a cosine pattern? I make use of the cos theta representation and assume that um is the maximum value of the radiation intensity or the power which is present over here. And how do I identify that the antenna is bidirectional? I make use of the theta value, theta for complete range from 0 to 180 degrees or 0 to pi radians. So theta will be varying from this range, and phi will be varying from 0 to 2 pi. So these are the conditions which specify that it is a bidirectional cosine pattern. And based on the plots what we have, we'll be obtaining, say if theta is considered as 0 over here, I'll be getting a pattern which is 8 shape. And if theta is equal to 0 here, I'll be getting a pattern which is infinite shape. That is pattern which will be like this, that is as infinity. Now here, when we are solving the problem, again we make use of the concept directivity is given as the ratio of maximum radiation intensity to the average radiation intensity. In this case, this average radiation intensity is nothing but the radiation intensity which is emitted by the isotropic antenna. And if U naught is the radiation intensity which has been emitted by the isotropic antenna, then by application of power theorem, we have the total power which has been radiated by this antenna as 4 pi U naught. Now what we have to do is we have to apply power theorem to the given condition, that is to this condition. We have to apply power theorem to this condition. So now under this case, what we have power theorem given as the double integration of u with respect to the solid angle. So in this case, we have d omega, which is sine theta, d theta, d phi, and we have u over here. We substitute u as um cos theta, and this is the rest of the part, that is sine theta, d theta, d phi. Theta will be varying from 0 to pi, and phi will be varying from 0 to 2 pi. So here, what happens is, if you apply this method over here, that is, if I make use of this, if I simplify this, what happens is I have sine parameter over here. I have sine parameter. So sine is a even function. Sine is a even function. And when you take 0 to pi, say based on this one, I take sine 2 theta d theta. So if I integrate this, what happens is, if I take the limits, I'll be ending up with the results which will be evaluated wrongly. So for that purpose, what you do is you can apply the concept of, say, the even function. So based on that, you can apply the concept. So in order to do that, what you can do is you can change the limit. since sine 2 theta, which we have applying over here, it is even function. So what we can do is, for even function, if I am having, as I mentioned, if I am having a function x of t, and x of t is even, and if this limit is 0 to pi, if x of t is even, then I can change this integration to 0 to pi by 2 x of t dt. So I can obtain the result of this equation in this form. So this is one careful step what you have to look forward when you're dealing with bidirectional cosine pattern. So just be careful under this case. So here what you do is you apply the concept of even function, and you take the integration as 2 times integration of theta is equal to 0 to pi by 2 sine theta cos theta d theta. This is nothing but sine 2 theta itself. This is nothing but sine 2 theta itself. So here what you do is you solve the integration, and when you solve the integration by using this method, what happens is you will be getting a value in which the total power radiated will be 2 pi into um. If you want, you can try out this method. You'll be ending up with 0 over here. So you can just check out this solution. So which is wrong. So just be careful in this part. Bidirectional cosine pattern. So for this case, in order to simplify the integration, right, use the concept of even function and try to solve the problem. So when you solve this problem, you will be ending up with the total power which is being radiated as 2 pi times um. So now we have the total power which is radiated by the bidirectional cosine pattern, and the power which is being radiated by the isotropic antenna which you have considered. Now we equate the equation 2 and equation 4. So when we equate both, what we'll be having is 2 pi times equal to 4 pi times u naught. That is due to the isotropic antenna. And when we cancel off the terms, we arrange this in terms of by u naught. So when we arrange it in terms of by u naught, what we'll be having 2. So this is the directivity of the antenna with bidirectional cosine pattern. Bidirectional cosine pattern. So next we have two other conditions. So I'll just give you the hint of how to go ahead. So here we have a source with sine power pattern. Source with sine power pattern. Now sometimes what happens is we can specify, instead of bidirectional, we can specify that the pattern is donut shaped. Pattern is donut shape. So if you just look at the pattern, right, in 3 dimension. So here you can observe. So this, if I slice it, and observe, say from this direction, if I slice, I'll have a 2D pattern which will be showing only these two circles. So that is what is represented in the back and over here. So which is infinite shape. And if I observe it from this end, and if I slice it over here, here also I can see that it just shows me the two circles. So this pattern, what is shown over here, this, if you just observe, and from top, if you observe, you can observe only the circle. You can observe the circle. So in 3 dimension, if you just see, it is donut shape. It is donut shape. So sometimes what happens is, for sine pattern, they specify that they specify that sine pattern is having donut shape. Sine pattern is having donut shape. So this is when you consider theta along this direction as 0, and here 90, and here 180. So if you consider this and plot the values, right, you will be getting infinite shape pattern. So, and when I observe this pattern, right, in 3 dimension, it will be donut shape. So sometimes this, instead of bidirectional, they might use this term donut shape. The pattern is in donut shape. So this is, you have to identify that the pattern is bidirectional, and in this case it is given as the pattern varies according to the sign variation. According to the sign variation. So again, since donut or bidirectional, it is identified by what? It is identified by theta is equal to 0 to 180 degrees. And since it is sine pattern, it is identified by sine theta. And phi is still in the range of 0 to 2 pi. Now again, in order to identify the directivity, what we do is we make use of d is equal to by u naught. So now I know what is the radiation pattern. I try to identify uh, what is the total power using the power theorem. So in which we integrate u with respect to the solid angle, that is d omega, which is sine theta d phi. So for this case, theta is in the range of 0 to pi and phi is in the range of 0 to 2 pi. So what we do is we substitute those limits and we simplify the equation. We simplify the integration. So when we simplify the integration, we get the total power which is being radiated by the sine bidirectional power pattern is pi square into And if U naught is the radiation intensity of the isotropic antenna, the total power radiated will be given by 4 pi U naught. Now we again equate these two equations. We equate these two equations in which we have pi square is equal to 4 pi U naught. Make the cancellations and we observe that by U naught is 4 by pi, which is 1.27. So this is the directivity of antenna which is having sine power pattern and which is having donut shaped or bidirectional form. So this is for sign variations. Okay. The same problem, again, we have done bidirectional sign pattern, which is nothing but donut shaped sign pattern. So again, the same thing is considered. Okay. The same way we have solved it, we'll be obtaining the same solution. So we can have different possibilities under this case. So here we have bidirectional sine squared pattern. We can have bidirectional cosine squared pattern, unidirectional cosine squared pattern. So any patterns we can provide. We can have a pattern which is a combination of sine and cos, which is combination of both. So if that is the case, you have to try to follow the same steps and try to obtain the relation by u naught and try to obtain what is the directivity. Okay. So these are the different possible this thing which can be given. So here we have given source with unidirectional cosine squared pattern. Cosine squared pattern. So since it is unidirectional, again theta will be in the range of 0 to pi by 2. And rest all steps will be same. If it is bidirectional, it will be in the range of 0 to pi. So these are a few things what you can look out for. You can use the different equations to simplify the integration. That is, you get these terms regularly. Cos multiplied with sine. These terms you get regularly. And since you are looking over here, say 0 to pi by 2. So what happens is generally you have integration of theta in the range of 0 to pi by 2 and with cos and sine this thing. So if you want, you can simplify this or you can use the beta and gamma functions. If you remember, you can use the beta and gamma functions. If you use this integration will be very simple. No need to do substitutions and other things. Just try to utilize these things. So if you utilize this, it will be pretty simple. So this is beta and gamma functions what we have given. So if I have an integration in the range of 0 to pi by 2 cos raised to p theta sin raised to q theta d theta, I can apply beta function to this. So which is given by this integration is equal to half of beta into p plus 1 divided by 2 comma q plus 1 divided by 2. Now this is nothing but beta of say m comma n, which is represented over here, which is equal to gamma of m into gamma of n divided by gamma of m plus n. Now in this case, we have to remember one thing: what is gamma m or gamma n? So here we have gamma n, which is n minus 1, its factorial. And when we come across gamma of half, it is, I guess, it is square root of pi, or it is pi. Gamma 1 by 2 is square root of pi, I guess. So you can utilize these things to simplify these integrations. Because if you go for higher powers, right, it becomes really difficult. If you go for cos cube, sine cube, so you can apply the simplification, but if the power goes on increasing, it becomes really tedious to solve the integration. So you can use beta and gamma functions. Okay. So this is all for today. Let us meet in the next session. Thank you.